Transformers are capable of receiving AC power at one voltage and delivering it at another voltage. In this way, they help achieve better transmission efficiency while transferring the power over longer distances. From the generating stations, transformer is used to step up voltage. Power then flows through the transmission lines. Then, transformer is used to step down voltage to serve customers. In this video, we will go through the characteristics of practical transformer, operation, and standard ratings. But before anything else, I would like to introduce myself. I am Lance Jasper Okutab, and please don't forget to hit like, comment, share, and subscribe. And don't forget to hit the notification bell for more videos. So, without further beginning ado, let's begin with the characteristics of practical transformer. First, it uses electromagnetic induction in transforming voltage levels. Second, the input and output power of a transformer has the same frequency. Third, the electrical machine is static, therefore there are no losses due to air resistance and friction, unlike electric motors. Fourth, it has copper losses since the windings are electrical wire with resistance no matter how small. And lastly, it has core losses due to eddy currents and hysteresis losses. So the basic working principle of a transformer is simple: electromagnetic induction. According to this principle, a varying magnetic flux associated with the loop will induce an electromotive force across it. Such a fluctuating magnetic field can easily be produced by a coil and alternating EMF system. A current carrying conductor produces a magnetic field around it. The magnetic field produced by a coil will be as shown in the figure. With the fluctuating nature of the alternating current, the magnetic field associated with the coil will also fluctuate. This magnetic flux can be effectively linked to a secondary winding with the help of a core made up of ferromagnetic material. This fluctuating magnetic field will induce an EMF in the secondary coils due to electromagnetic induction. Since the turns are arranged in a series, the net EMF induced across the winding will be the sum of the individual EMFs induced in each turn. Since the same magnetic flux is passing through the primary and secondary coils, the EMF per turn for both the primary and secondary coils will be the same. The EMF per turn for the primary coil is related to the applied input voltage as shown. As a result, the induced EMF at the secondary coil is expressed as follows. This simply means that with fewer turns in the secondary than in primary one, can lower the voltage. For the reverse case, one can increase the voltage. But since energy is conserved, the primary and secondary currents have to obey the following relationships. The core of the transformer is made up of thin insulated steel laminations. Such steel laminations are stuck together as shown in the figure, forming a three-phase limbs, well depending on its application. The purpose of thin lamination is to reduce energy loss due to eddy current formation. The low voltage winding usually is set near the core. Various kinds of energy loss happens while transferring power from the primary to secondary coil. All these energy losses are dissipated as heat. Principle of operation of a transformer. Voltage ratio of a transformer is equal to A, where A in voltage ratio is equal to the ratio of primary to secondary voltages, and A in number of turns is equal to the ratio of a primary to secondary number of turns. On the other hand, the current ratio of a transformer is also equal to A, where A in current ratio is equal to the ratio of secondary to primary currents, and A in number of turns is equal to the ratio of primary to secondary number of turns. For example, a transformer has 500 turns of the primary winding and 10 turns of the secondary winding. Determine the secondary voltage if the secondary circuit is open and the primary voltage is 120 volts. To solve this task, we use the fact that the ratio of the voltage on the secondary and on the primary coil is the same as the ratio of the number of turns of both coils. So we evaluate the unknown secondary voltage. Then we substitute the given values and we get 2.4 volts in the secondary voltage. Standard ratings of transformers. Voltage rating. It is important to know the voltage rating so that to protect the winding insulation from failing because of an excessive voltage applied. At the same time, to have an idea about the magnetizing current and its magnetization curve of a current transformer. Frequency rating. The most commonly used frequency ratings are 60 Hz and 50 Hz. In our country, Philippines, the standard frequency is 60 Hz for electricity grid. Next is apparent power rating of a transformer. The primary purpose of the apparent power of the transformer is to set the current flows through the transformer windings. The heating of the transformer coils depending on the current flow through it. The apparent power rating of the transformer has to account for the nature of the load since loads are not purely resistive. For example, a 100 megavolts ampere transformer can serve a maximum of 100 megawatts purely resistive load. So, as I said earlier, loads are inductive in nature. Therefore, if a load with 0.8 power factor, that means that 100 megavolts amperes has to be multiplied with the power factor 0.8. So it equals to 80 megawatts real power and a 20 megavolts ampere reactive power. Thank you for watching and stay tuned for more videos.